So what do we notice, first of all? Well, Ray, what's the point of this whole analysis? It's to figure out what's important in the problem, or to come up with an approximate answer for the problem. So we can look at this and say, first let's look to the right. So he can come in here, right? He can come in here and it can go to the right, or it can go to the left. So if it goes to the right, what's it going to do? Well, my radiation resistance is really, really high, right? 1758 compared to 270, right? 270 up here. So if it has to choose a path, the heat's going to come in and it's going to go to the path of least resistance, right? Which is up here. So almost all of the heat, by probably about an order of magnitude, is going to be going through the convective side. Very little heat is actually going to be radiated away. Okay, so that's number one. The other thing is, what about the heat that could go to the left? Right. Well, we have over here these different resistances in series: 5.4, 4.18. Right. You can basically say, okay, I'm pretty much going to neglect what's happening here in the spreader. Like the conduction in the spreader, it's a really conductive material, so it doesn't really affect things that much. Conduction through the chip is also pretty small. So really we're dominated by convection to the water and conduction through the dielectric. All right. If you go to literature, actually, you're going to see a lot of the work in this area has to do with finding better dielectric materials and better heat transfer on the convection side. So just by doing this basic analysis, we can filter down the area that we want to spend more time. And this is where people are spending their time. Okay, the other thing we want to go back and double check was I put in a guess. So my guess was probably wrong. So when I go back and solve this, I can just add an equation that calculates TC directly. Okay, so TC directly can be calculated using an energy balance. And so let's look back here. So if I do an energy balance on this node here, I'm going to have G dot coming in. And what am I going to have leaving? Well, I'm going to have heat flowing to the left. Right? Heat flowing to the left is going to be given by T, let's call this TC here. Okay, so TC minus TW over the total resistance to the left. Right? The total resistance to the left is all these things in series. R convection, W plus R conduction, S plus R conduction D, plus R conduction C, right? That's the heat going to the left. What about heat going to the right? Sorry, I'm kind of out of room here, so up here. Q dot to the right, well, that's going to be equal to, again, TC minus TA now, right? And just let's keep track of the way I'm drawing. I drew the arrows where you have energy coming in here, energy leaving here, and that energy balance has to match. The sign of that energy balance has to match what I drew, but the order of the temperatures that I'm using also has to match, right? So I drew it in from TC to TA, so it should be TC minus TA. Right? Same thing the other way around. Okay, so TC to TA divided by, well, what's the total resistance to the right? Now we have two resistances in parallel, not in series. So how do we write that? And so it should be, you take 1 over each resistance, right, that you have. So R convection A plus 1 over R radiation A, and take the inverse. Take any or all resistances you have in parallel, take the inverse of them, add up the inverses, and then when you're done with that, take the inverse of the whole thing, right? And that's your parallel resistance model. Okay, so that's to the right. So we'll take all that stuff, put it in an energy balance, which we did here, right? So here's our energy balance. We're saying G dot has to equal, right, coming in has to equal what's going out. So TC minus TW and all that stuff in series, TC minus TA, and then our convection and radiation in parallel, right? So we can use this equation. Everything here is known except for TC at this point, where we solve for all of our resistances. Everything's known, so we could solve now for TC. Okay, and here we are with, this is our calculated TC value, 68.54. this is what we guessed over here. This is what's being used for our radiation, right? They're not the same value, right? They're not that far off, but they're not the same value. So to really get the full complete answer, we just go back here, comment out our original guess, okay, and then assign the guess value to be the actual value we solved for, and then the resistance is going to be recalculated, like in real time as we're solving this. So if I solve this, you know, it's a pretty simple problem. It might solve. Let's just try it. Okay, so it's solved. Half the time, though, you might get an error. It might fail to converge. So really what you want to do is you solve it with this uncommented, and then you come up here to the guess values. Like this little G, it's almost impossible to see. It says update guesses. So you can click that. And ease will then, instead of starting everything at 1 with its guess, it's like iteratively solving, right? Instead of everything starting at 1, which is the default guess, it'll then have a much better starting point for its solution. So if you don't do this, what it's doing is it's gonna guess 1 for all the temperatures, right? So it's starting with a temperature of 1 Kelvin, pretty much. And then it's gonna try and iteratively come to a solution. Many times it's too far away, you can't do it. So it really helps to update the guesses this way. In this case, it happened to work. So we'll do this, we'll update our guesses. And we see now that our guess matches exactly our calculated value. And okay, the magnitude of the resistances didn't really change that much. So turns out our approximate guess was okay. All right, let's see. Yeah, any questions on that part of it? I think pretty straightforward. But yeah, again, this is kind of a cool technique to get a handle on things. All right, so we have now our guess temperature exactly matching. We went through this process. And by the way, you know, one thing that kind of an aside here, this looks really easy to do. Like physically, all we're doing is uncommenting an equation and commenting something else. So it's really easy for us to do. But if you're not using ease, how would you actually do this? Or you'd have to write a program that does all this. Say you're doing it in MATLAB, or you're doing it by hand, or God forbid Excel, right? So you're doing all this. You get to this point where you have this guess, but the guess is something you've entered as an input, right? And so now, how would you actually solve this? You'd have to do this calculation, calculate the new temperature, and then go back and reset the temperature manually, do the calculation again. There might still be a gap, so then you go back and redo it. So you iteratively do this. Like before computers, people would physically sit down and write out 10 pages of iterations for something trivial like this. So we actually just did something that was pretty complicated by commenting and uncommenting these equations, but because of the way we're solving this problem, it's pretty simple. Okay. Just want you to kind of have some degree of appreciation for that. All right, cool. So let's move on a little bit here. All right, so we have our model. Let's see, what was this? I was just going to annotate this a little bit. Let's see here. All right, so one thing that we did as part of this is we wanted to solve for the temperatures. We look back in our ease program, we actually calculated the temperature, right? And it was 3 something, which is actually 68.5 degrees Celsius. For a chip, that's probably okay. 60, that's much less than boiling. The plastic's not going to be melting. The solder's not going to be falling off, right? You're probably okay. So we did this simple model, but we made some assumptions as we went through this, right? And they were kind of important assumptions. One, you know, we could try to list out what the assumptions were. One, we said generation is occurring at the surface, not within the volume. The other was that we said, actually, if you look at this material here, we said heat that's flowing in from the chip into this spreader, we just assumed, let me just actually draw it. So we just assumed that the heat could come in here and go over and use kind of the full width of this, right? Which is why we call it a spreader. So we're saying magically the heat, once it went into the spreader, had the full area available to it to conduct. And that's kind of not true, right? There's a resistance associated with getting heat from here over to here, right? Same as there's a resistance associated with getting it across the thickness of this layer. So when we said that, we have this full area available to us, we have to understand is that assumption, I don't know how to characterize it. Is that a conservative assumption, or is it an aggressive assumption? Does this model give us an upper or lower bound on our resistance? Okay, so let's see. We went through this process, and this assumption, we're going to give this a name. So we call this the isothermal limit. Right, in the isothermal limit, we assume that that the body's isothermal, right? We assume that the spreader in this case, which is where there's a step change in area, we assume that remains isothermal, and there's no additional resistance associated with the heat moving isothermally. Okay, the isothermal limit actually gives us one of the bounds on our problem. Okay, what would be the alternative to the isothermal limit? Well, over here we could say heat that's coming in here, it can only move in this direction. Okay, and that would imply then that this whole region over here is not involved in the heat transfer. Okay, we would call this the adiabatic limit. All right, so the adiabatic limit now says when we're conducting, we only have available to us this width, which is WC. This width over here is WS. I believe WS was 2 centimeters, and this is 1 centimeter. So we only have a fraction of the area available to us for heat to actually flow through it, and the rest of it is not involved. If we really wanted to be aggressive, we would say, not only can I not conduct, but I can only convect, right? So I could only convect from this surface in this area. Because if the heat's not moving out to the edges, then there's no temperature difference between the edges and the surroundings, and so it's there's no heat transfer. So if we carry that assumption all the way through, then now we have to go back and recompute in the adiabatic limit what the alternate resistances would be. Okay, so let's get back and think about what is this giving us, right? The isothermal limit is actually giving us a lower bound on resistance, or let's say R total. Okay, a lower bound on R total. That means we're being aggressive in the areas that we're assuming. The areas are larger, that means the resistance is lower. On the other hand, the adiabatic limit would give us an upper bound on our total. Okay, and if we solve both of these problems, we can make either assumption. We can solve the problem both ways. And we're going to get 2 different temperatures. We're going to get 2 different sets of resistances. And we can then say, all right, I know that my real problem has to be somewhere between the isothermal limit and the adiabatic limit. Like, it's not perfectly one or the other, it's somewhere in between. But if I have a window, and everything in that window, or the bounds of that window are still okay, I'm done, right? Then I don't need to do anything else. Okay, so let's go back and solve the problem this way. So let's, in ease. All right, so back here in ease, right up here I have my isothermal model. Down here I entered in some equations for an adiabatic model. So let's get this to work. Okay. So my adiabatic model, I solved it the same way. Right? I put in our conduction, adiabatic, our convection, adiabatic. These are the only 2 that are changing. That was, I don't have it up, but that was the conduction through the spreader, and then the convection from the bottom of the spreader. Everything else is staying the same because nothing else is subject to these assumptions. Okay, then I had a guess. I calculated my radiation. Redid the energy balance. The G dot's still the same. The only thing that changed here was I'm using my adiabatic temperature. I'm going to solve for a new chip temperature as if the adiabatic assumption is in place. Okay, and again, everything else is the same. Note though that here we're using, for the spreader, where we're using WC, just the chip area, not the spreader area. Same thing for convection. By the way, this is an aside again, but if you hit, I think, F10 in here, you can actually have the formatted equations windows, and sometimes it's easier to look at stuff. It's kind of hard to look at equations that aren't formatted sometimes, so this can be a nice way of writing. And I think you can actually copy, so I know I use LaTeX to write stuff quite a bit. You can copy this stuff as LaTeX. I think you can also copy it, see if you can copy it as just like math type as well. Yeah, so if you want to like copy these equations and paste them into Word as you're writing up your summary or writing up your methodology, it's really easy to do that in ease. Just kind of a nice tip. Okay, so that was F10 to get to that, or you can go Windows equation, formatted equations. All right, so here we are with our new energy balance. We solved this. And what do we get? We get, let's see, TC is here. And then we are looking for our TCA. Where's that? TCA. Am I blind? Where did it go? Did I miss it? The big thing with the box over it? Perfect. Okay. There's moments when you feel really old and you're not actually old. Okay, so what is this telling us? So our adiabatic limit is telling us 141, right? So just that one assumption, it made a pretty big difference in the temperature. Now, is 141 a problem? I don't know. I'm not making the chip. I'm guessing it's probably not. But you know, it's going to be something that you have to think about. If it turns out now the material is rated to 200 or 250 or something, and there's no safety concerns for people touching it or whatever. Like this, at this point now, we've proven that these are the bounds. Right? It can't be any worse than 141, and it can't be any better than 60, whatever it was. And at this point now, we've done our job. We're done. We don't need to do any more. Okay. So again, useful tool for bounding, but isothermal limit, adiabatic limit, those are both underlying assumptions that we make.